Thank you. So my name is Raoul Schaffranek. I work for Runtime Verification, and I'm a formal verification engineer there. And today I want to talk a little bit about what formal verification actually is and how we are working on making it more accessible to individual or to developer teams and to individual independent security researchers. So at Runtime Verification, we used our tooling to formally verify the ETH deposit contract when Ethereum went through from the proof of work to the proof of stake consensus mechanism. We formally verified Uniswap, Lido, Optimism, parts of EigenLayer. So, but you know, all these are big players. But and formal methods, formal verification has been proven to be useful to harden your security. But we need to make it more developer friendly so that everybody can use it. And this is kind of the topic of my talk, really. So, if you have not heard of formal verification, today I'm going to talk about a specific flavor of formal verification that's called symbolic testing. And I want to think you about symbolic testing just as a way of increasing the confidence that you have in your test suite. So in a similar way that fuzzing or property testing improves the confidence over unit testing, symbolic testing is just a logical next step to make your test suite, to increase your confidence in your test suite even more. And it's actually, at the upper hand, it can give you very strong correctness guarantees that I will talk about in a minute. So if you are familiar with fuzzing, then you are in a very good position to understand symbolic execution. So when we are talking about fuzzing, we basically mean we have a test suite that's usually written in Solidity, and then you leave some of the parameters, in your tests. And what the fuzzer does, it throws random inputs at your test function, and then it tries to find counterexamples. So, and at the end, the fuzzer tells you, hey, I found a counterexample, which is really nice, because then you know you have a bug, and you need to go back to your smart contract, fix this bug. You can just run your fuzzing suite again, and eventually the fuzzer will at some point say, okay, your test passed. And, well, this test passed is a kind of where we, from a formal verification perspective, get really paranoid, because what it's actually telling you is, I'm not sure. I just couldn't find a counterexample, but I have no guarantee for you that there is no counterexample. Maybe you just need to fuzz longer. So maybe you just need to fuzz for 24 hours or for a month. And I actually recommend do this. Like it's a no-brainer. If you're interested in security, just set up a fuzzer that is running on a server that fuzzes your code base 24/7. Why not? It's really cheap. But even if you do that for like 1 billion years, it has still no guarantee that there is no potential bug. So what is symbolic testing now? Symbolic testing also just takes a Solidity test, and it executes the test not on random inputs, but it executes it on abstract states. So, and now the cool thing here is, instead of a fuzzer, you have a prover, and the prover can either say, hey, I found a counterexample, so great, you need to go fix your smart contract, or it says, I have a proof that no such counterexample can exist. And that's really a rigorous mathematical proof that this is literally impossible. Or the prover says, you know what, I'm not sure, I don't know. And then you need to guide the prover, you need to provide some custom lemmas and tell it how to make progress. So, and the ultimate goal is, of course, reach this green state, like have proofs that your smart contract actually satisfies your test suite or your specification. And a problem with formal verification at the moment is that, well, the developer experience is not that good. Mostly command-line tools that give you cryptic error messages. And we are building a new tool, which is a symbolic Solidity debugger. So, and this tool is actually the first like visual symbolic execution engine. And you can learn like gradually. Like I know this space needs a Solidity debugger so bad, right? And this one is integrated into Visual Studio Code, and you can just use it as a classical debugger. So you can set the breakpoints, you can step through the code, all of that stuff. You can even go down to the bytecode level and step over one bytecode instruction at a time. But the killer feature is really that it also has this symbolic execution mode, and this symbolic execution mode visualizes symbolic execution for you, so it becomes a gradual learning curve. Like if you know how to use a debugger, then you can gradually make your initial state or your test cases more symbolic, and then by that increase the coverage of your debugging session. So, and you can. We have a public online demo that you can go to trysymbolic.runtimeverification.com. You don't need to install anything locally for that. It just runs in your browser. You can see how it unfolds in front of your eyes. Okay, so let me take one step back and what is debugging? What is symbolic execution? Debugging is, other ecosystems have it. Like ThreadFi has it, Java has it. You set breakpoints, you step through the code, you inspect the states of the variables. It's really just, I like to think of a debugger just as a guide when you're reading code, because, well, I was doing audits a lot, and I was executing programs on pen and paper, actually, so making sure that I cover all the branches and stuff. So then I figured, well, a debugger would be so nice. It can help me so much time. It can save me so much time. So now symbolic execution is a way of exploring the state space of your smart contract systematically. So that means you have some, during the execution, you will have some abstract states. So instead of, for example, you have a balance of Alice that's 100, you say the balance of Alice is just X, and you don't know anything about X. So, and when you do this, that means there's sometimes your code can take different paths because it does not know enough about the balance of Alice. So it can branch. So instead of having like a linear stack trace, you now get an execution tree or a control flow graph. When you're done symbolically executing, you either get a counterexample, or you get a proof of correctness, or it gets stuck somewhere. And this stuck is really where things are getting messy and where you need to dig deeper. Symbolic also has we just launched an offline version of Symbolic, an online version of Symbolic that you can just install from your Visual Studio Code. This version on Visual Studio Code on the marketplace has not the symbolic execution features built in yet. We are working on that. But this is just a classical debugger, and I assume this is a useful tool in its own, even if it cannot perform the symbolic execution yet. So we are currently trying to merge like the symbolic execution mode and the concrete execution mode. If you still don't get what symbolic execution is, just trust your intuition, really, because symbolic execution, don't try to read an academic paper about it. Like, these are very condensed and very deep and super hard to read, but actually you are a very good symbolic executor like already. So whenever you're reading code, basically, really, every time you're reading code, you are symbolically processing it in your mind. So let's take this example snippet. So this snippet could be part of a transfer function. So it first checks, hey, is the balance that we want to transfer, does it exceed the balance that I have? And then it's reverting, or in the other case, it's transferring tokens from one address to another address. So now if I tell you, to execute this code mentally from this initial state, where we don't know what will be the receiving address, we don't know what will be the sending address, and we don't know what is the value that we are going to transfer. But we know that whatever this address, the from address is, has a concrete balance of 100, and the receiving address has a concrete balance of 200. So now I ask you, okay, from this initial state, execute the if statement. And what you notice is that in the if statement, we don't have sufficient knowledge to decide if we need to take the then branch or the else branch. And so what you do is, okay, you first consider the case where you go to the then branch, and then you make a make a little mental note in your head that you still need to look at the else branch later on. But let's first look at the then branch. And we've learned something about the value now, because now we know that the value must be greater than 100. Otherwise, we wouldn't be in this branch. So this is what we call a path condition. And then the next statement that you would execute is this revert statement. So the transaction reverts, nothing interesting happens afterwards. So we are done with the then branch. And now we memorized, we had a little mental note on the else branch. So we still need to check the else branch. What we do is, okay, we now know that the value must be less than or equal than 100. We are executing the storage updates one step after another, and then we are done. So, and I did this very slowly, but I bet if you're reading this code, you can just do it within like some seconds. And that's really I'm just saying this because you are an excellent execution engine mentally. Let's talk a little bit about the EVM. You may have heard that EVM is like a state machine. And if I'm not mistaken, the initial state, like the Genesis block, was mined in 2015. And well, basically at this state, there were no smart contracts. Everybody had a balance of 0, basically. And then we did like lots of transactions. People deployed smart contracts. And here we are currently at this time. And we know, so we have recorded like a lot of transactions. They all changed the state. They changed the balances of the users. New smart contracts were deployed. And a state is really just all the account balances, all the storages of the smart contracts. That's what our state is. And every transaction changes the state in some way if it does not revert. So now here we know that some of these transactions have been exploiting bugs. Well, and that sucks. So, but well, it happens, and most of the time there's not much that we can do about it. But we can do something about the future. We can try to make our smart contracts more secure and find these bugs in the future. So the problem is now, well, we cannot predict really what will be the next transaction, and what will be. So there's basically an infinite amount of choices for the next transaction. And even if we could predict just the next transaction, well, the game would repeat afterwards. So you have this huge, ever-expanding state space, and you know that, well, some of these states might be buggy, they might be exploitable. So what's a systematic way of finding these buggy states in your smart contracts before you deploy them? And what we do, I'm going to skip this slide. What we do is basically, with symbolic execution, we make it possible to explore the entire state space. So, and this entire state space, it will include the buggy transaction. And so you can actually see that it includes a bug. How are we doing this? Let's look at a simple example. So we are doing let's say we are doing a simple transfer. From Alice to Bob, we are transferring 10 tokens, or from Alice to Bob, 20 tokens. Transfer 30 tokens from Alice to Alice. And every transaction would lead to a different successor state. What we're doing, so if you just, maybe one of these transactions has a bug in it, right? So, and if you're lucky, you have a test case, or you have a fuzzing test, or you ran a debugger and you found this bug. But there's no guarantee. The space that you need to explore is just too big. So what we do instead is we execute a transaction from an abstract state. So instead of saying we are transferring from Alice to Bob, we're just saying we are transferring from somebody to somebody. And these somebodies are just variables. It's $from and $to. And we don't make any assumptions about their balances. We say, it's X and Y. And then we make an abstract transaction, transfer from, we are transferring like some value from some address to some address. And then now we only get 2 possible successor states. The first successor state is, well, the addresses were different, So we credit the one account and we debit the other account. The other case is the addresses were the same, so the balances should actually not change. And executing transactions on an abstract state with abstract inputs, that's symbolic execution. So you can actually collapse like an infinite possibility of transactions into a single abstract transaction. Now, if you think about fuzzing, there's also one of the problems is you usually fuzz only one transaction. There are some fuzzers that can do multiple transaction fuzzing, so they randomly generate one transaction and then they generate another transaction that follows after. It's sometimes it can find bugs, but still your state space is so huge. So what we do in symbolic execution? We do something that mathematics like to call structural induction. And this structural induction basically allows us to execute a transaction from an arbitrary state, and it will end up in an arbitrary state. So we don't need to generate another transaction at the end because we know that whatever follows this state could be subsumed in the initial state of the proof of the first transaction that we executed. I'm sorry if that is not very understandable, but the thing here is the thing that you need to take away from this slide is if you're doing symbolic execution, you actually don't need to do multi-transaction symbolic execution. It's sufficient if you just do one transaction, and it will be generally enough to cover all the possible states that they want to cover. So in essence, we reduce this problem of an ever-increasing state space that you need to explore to just one single abstract transaction that you need to explore and that you need to test or to debug. So that's a huge achievement. It gives you so much greater confidence in your smart contracts because now you know, okay, now you have the peace of mind that your fuzzer didn't say green just because it was not fuzzing long enough. So you actually get a proof that this cannot exist. Temporal granularity, I'm going to skip over this slide because I'm running out of time. Let's look a little bit at the user interface of our debugger. So as I said, the states are basically all the storage and the account balances and stuff, but that is only at the transaction level. So if you look at the state before transaction and the state after transaction, okay, this will be your state. But during a transaction, there will be additional states, like your EVM state. There will be a program counter, there will be a stack, there will be memory. And our debugger basically allows you to look into all these low-level state components of the Ethereum virtual machine. And it gives you basically a full view of what's going inside in your virtual machine. From a classical debugger, you would also expect that you are able just not to look at the low-level data, not just the memory, not just the storage, but you also want to look at Solidity variables, right? And we are working on that. The problem at the moment is a bit that the Solidity compiler does not generate sufficient information for us to decode variables reliably. But the Ethereum Foundation is actually working on what they call the ETH-debug format, and we are kind of waiting for this format to land in the compiler so that we can actually do reliable variable decoding, and then it will be even easier to use. What's our roadmap for Symbolic? We just released an open beta version, so I told you about this website, try.symbolic.runtimeverification.com, and this is the Symbolic execution version that runs in a browser. It's very limited demo, to be honest. But we also have this, just the classical Solidity debugger, and it's available from the Visual Studio Code Marketplace. You have steps through debugging, you can do it on the bytecode level. And we are really working on a good Foundry integration so that you can just debug your Foundry tests. I put this under the one column here. It's not ready yet. Implementing Foundry cheat codes is something that takes some more time. Our next step is, well, part of Symbolic is open source, so the Visual Studio Code extension is fully open source, but there's some components that currently run on our service. And we eventually want to make these other components also open source as they become more stable. Then we want to make it even more convenient for users to use and really to look at the state exploration tree. So there will be a nice graph visualization feature. And then, just as I just said, we are working on the ETH-debug format. And then eventually, we want to make this debugger also able to debug on-chain transactions. So one last thing is, formal verification is mostly used in the context to prove program correctness. But it also allows us to build an entire level of new applications. So you might have heard that formal verification proofs are like compute intensive, and that's true. Finding these proofs is very difficult, and it takes time. It can take hours. But once you have the proof, you can actually verify it really quickly. It's a different complexity class. It's really simple to do that. And we have a proof checker for our proof objects that just not even 200 lines of code. And that enables us basically to put formal verification proofs of program correctness on chain. Now, these proofs are still very big. So you don't want to put them on chain as they are, but what you want to do first is you want to snark them so that they become constant size. And yeah, I'm very happy Ilya from Pi², who will be speaking after me, is doing exactly this. So that's a great company, and they are building really a new kind of infrastructure for blockchain that enables entirely new applications. And they are using formal verification to do this. All right, that's all I've got for today. I hope it was not too confusing for you all. Please try out this debugger, install it. If it's not what you expect it to be, then we are very early in development. We literally just released it 1 week ago. So if it's not what you expected, talk to us, and tell us, what do you want from a debugger? So we are very flexible in prioritizing features. And if you have an idea for a cool feature, yeah, please let us know. So, and all this, open source development depends a lot on, benefits a lot from community contributions. So I would be very happy to talk to you all. Thank you.
We have time, Raoul, we have time for Q&A session. If
yeah,
you're open towards it.
That's great.
So if there's, yes. Oh, Mike is on the way.
Thank you. Can I ask 2 questions?
Yeah.
I have a quick one. When you said you have open source on the roadmap, are you open sourcing the prover as well?
The prover is actually open source. Oh, wow. So that's one of the components that's open source. It's called the K prover. So we are building on top of what's called the K framework, which is a very general theorem prover specializing on proving stuff about programming languages and virtual machines. So you can, yeah, it's completely open source.
I'm surprised because I know Sartora is not open source, and so I was
yeah, exactly.
Amazing that you have it.
So you can actually, and we have another tool that's called Control, and that is basically just symbolic testing. So it's a combination of Foundry and symbolic execution. So you actually can use Control is completely open source. If you have a Foundry test suite, you can just run Control on top of it to get really to hammer out all the edge cases. It's a very nice user interface. It's not perfect, but it's completely open source, and you can actually run it on your own CI pipeline if you want to. So that's a great thing of making sure that your code base stays intact.
Awesome, thanks. And my second question is about the, well, I didn't try it yet. I have a quick question, maybe I will get the answer. But you mentioned that testing transaction, debugging on-chain transaction is something you are working on. And I'm curious, what's the difficulty? How is it different, any different from testing a local setup?
It's actually, well, one of the problems is that when you're debugging locally, we can just compile it with our own parameters. So we can actually, in some cases, we want to turn off compiler optimizations because either it's compiling too slow, or also compiler optimizations sometimes mess up the source maps. And for on-chain contracts, you always have optimized code, and optimized code is it's more difficult to debug than unoptimized code. But it's not really like, it's just taking time to develop it. It's not too difficult to do it, it's just taking time.
Does that answer your questions? We have one more question in the front. Please go ahead.
Great.
Yeah, the question is, can you like highlight the boundaries when you should do formal verification, because it's quite complex things, and how long approximately it takes? For example, for average code, like 100 lines of code, how long does it take to build the whole math model for that?
Yeah, so for example, how control works is you don't actually need to write a new specification if you have a Foundry test suite already. So this huge step that makes formal verification often very hard is you need to write a formal specification in some weird formal verification language. But now you can you can do it in Solidity. But yeah, compute is different. Like how long actually does it need to take to find these proofs? That can range from minutes to hours to even days, depending on the complexity of your smart contract. So I really recommend, well, you can do it for simple tasks on your own customer hardware, but it's definitely something that you want to enable on your CI pipeline, because then it does not block your computer. So every time basically you merge something into your master branch, you want to trigger control onto your CI pipeline, and then if you have time to wait another 24 hours before you deploy your smart contracts, then take this time. It's just another day, and maybe it will find a counterexample, and it can save you from losing lots of money.
Does that answer your question? Do we have time for one quick question in case there's someone in the audience?
Yeah, thanks. Hey. No? Oh, okay. Thanks for the presentation. And question is, what differ your debugger from Foundry debugger, for example? Because what I saw is the same. We can trace memory, stack, storage, etc. And Foundry has a very beautiful visualization of state. What's differ?
So the Foundry debugger is, first of all, it's a command line tool. It's a terminal user interface, and it's not hooked up to Visual Studio Code. Also, I think our debugger, well, it's very early yet, but one of the prime features that we are working on now is like the symbolic execution path. And I think that's nothing that is planned for Foundry yet. What are other differences? Well, we allow you to inspect the EVM state at a deeper level. So we're actually working on making like the full entire EVM state inspectable, every single component, every single bit. While the Foundry debuggers like taking a more practical approach, and they are mostly visualizing the memory and the stack. I'm not even sure if they visualize or if you can inspect the storage. I'm not sure. I don't want to say anything else. But our goal is really make everything inspectable.
And that's a wrap. Raoul, please give it up one more time for Raoul.